So, okay, we're recording. Perfect. All right, so today really is just rearranging formulas. We're looking at, this is 4B, our last unit, 1.3. So that's the section if you like to organize it. Basically, we're going to be given, and we're working with physics formulas today. We're given a physics formula, and we want to rearrange things so that we can, you know, if you wanted to isolate T, it would be because you were looking to see what's the temperature output when you have all this change in, you know, volume, pressure, the gas constant in moles will probably stay the same in a system, but you can isolate T because then that would help you just get that information quickly. Okay. All the algebra properties and rules totally apply. If I wanted to know what P was, right, isolate for P, I would just divide both sides by V. That would get rid of V on the left side, and I'd have it in terms of P. That's what we're talking about. Okay. When we get over here, it's going to be a little bit trickier. But oh, this is lambda. Sorry, guys. See that? That's upside down Y, or the person without an arm and head, or something else. Okay, so I want you to look at where we're starting with the ideal gas law, and let's see about isolating T. What do we need to do in order to isolate T? So just go right at it. I'd rewrite the formula here. PV is equal to nRT. This is a real functional lesson. Okay, it's very functional. Well, I'm just calling you guys since I have 9 students in here. All right, Adriana, what do you think? We're trying to isolate T. What's the first thing we can do?
Divide it from R.
Good. Divide what from R? Because I think I know what you're saying here, but if I divide T from R, I'd have to divide on both sides. Yeah, but that doesn't isolate T. Let's actually try to get rid of these 2 variables to get T by itself. So what's the first thing we can divide by? Because it's N times R times T. This is synonymous to when we have this, right? When we have 3x, right? We want to know x, we divide by 3. There just happens to be 2 other values. Good. So you went right at it. Good. So we got it. Let's divide by in R, that's our moles and our gas constant in R. It's going to cancel on that side. And what do we have left over for T? Got it right here. It's pressure times volume divided by the number of moles times the gas constant. Okay. So we solve for T. You could do that for each one of them. You could solve for, you know, the number of moles if you needed to know the number of moles in the system. So actually that, yeah, you would be able to figure that out. You could figure out any of them if you just isolate it. Okay, so now how is T affected when N doubles? So now we already have T set up with you know, this series of variables with operations going on will give us T. How are we going to rewrite this to start where we show that N has doubled? Why don't you go ahead and try to write that on your own and then check with your neighbor. What do you think? If you don't know, check with your neighbor. Eliana, you have to check with the neighbor. Is that okay? All right, good. What? All right. Looks like we have enough ideas, hopefully. Let's see. So I heard some good stuff in the back. What do you guys think? Okay. There's nothing else. Okay. What's another way that I can write this right here? What's another way? There's one other way. It really is this 2 on the bottom. How could I make that a value that's separate from the other variables? What do you think? Good. You think that? Or I could say 1/2 times, right? UV over NR. Because it was on the bottom, I could put the 1/2 on the outside. If it was on the top, I could put a 2 on the outside, right? Because if I multiply this over, remember with fractions, we multiply straight across, that 2 is going to be joined with that end if I multiply it back together. Okay. So now I have this going on. I'm going to go ahead and erase this for a second. But look at our new setup right here. I think we got to put something right here, otherwise we aren't really balancing this at all. So let's look and see right here. Actually, one second. So what we're really trying to do is keep the integrity of our original formula right here. So think of this, from this formula, what did we do to the right side of the equation from here? What do we do? What do we do? What's the difference between the right side over here and this over here? Times a half. Times a half? If we multiply this, if I was back at this original equation, I'd multiply by half. What else do I have to do? Multiply both sides by half. You see? So going back to the original formula, how do we go from here to here? I multiply that side by half. And remember, with algebra, what you do to one side, you do to the other side. Okay. So it was incomplete until we get here. Now it is correct. So what happens when n is doubled? We could say this. T is half. I'll just write that. That's not that word. Half. How? Half. Not enough. That's for sure. No, it's not. Okay, let's see what else we have to do with these. How is T affected when P is doubled? Let's do the same kind of approach. Let's look at our same starting point here. The halves are going to be gone because that was just for part 2. But what would happen if P is doubled? And I want you to think about this. If you had like one of the strongest pressure, kind of like the ones where they get a molten piece of molten piece of metal, and they have the pressure that will like push it into a form, right? What happens when something is pressurized and forced down? Can you give an example of what happens? It becomes smaller, the volume is going to be compressed. Now, what would happen if you kept compressing it, kept compressing it, kept compressing it, got smaller and 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 smaller? What's going to happen to it as well? Can you imagine? It will get super dense. Hard. Okay, dense, hard. That's good. All right, we're going to see right now. But I know a couple examples where this happens. Let's go ahead and actually play with it first. Let's go ahead and put what? P is doubled. So, I mean, now that we know the trick to this, we can actually do this pretty quick. If I double P, what's going to happen to time? We have to double as well. When you compress things, you end up raising the temperature of that. That's what I was trying to point out. Like if you hit something with a hammer, well, there's actually kinetic energy with that. But smashing something smaller and smaller will get hotter. It's like make diamonds. They actually make synthetic diamonds doing pressure. It's incredibly hot when they do that. Okay, so it's just going to double it. Really, this was pretty simple. It really is about rearranging this initial isolated T. And if we double P, then we have to double T to make it balance. That's all it is to it. Okay. I think from today's or this week's lesson, it seems like there's a lot more that we have to do with that. But that's the main thing we're shooting for here. Now, if we look at stringed instruments, let's see if we can kind of think about this for a sec. So the velocity of the wave is equal to frequency times the wavelength. Here we have the velocity of the wave also is equal to the square root of tension divided by mu. And we have mu is equal to, that's our mu constant, mass over the string length. The constant, I believe, is based on the material you use. So if you have copper strings versus steel string, you will have to accommodate that. So first, you see that this is kind of a world within a world. Okay. Mu is equal to m over L, and mu is right here, right? Velocity of the wave is equal to frequency times wavelength, and we have another velocity here as well. So again, we're trying to manipulate it. What are we trying to do? Create a formula for F in terms of m, L, F, little f, and lambda. So let's look to see how the heck we would do that. All right, we'll get there. What terms do we not need? It says in terms of these, M, L, F, and lambda. What are the ones that are left out from our initial equations here? What was that? Mu's out. Velocity of wave. So is there a way to substitute or move things around in order to get these two components negated out and we have all the other terms? Think about how you might do that. Can you see it? You see it? So we know we don't want, I like to see, okay, what do we want not included? Because then I look to see if I can substitute something, get rid of it. So I know mu is m over L, right? So where can we put this? Right there. So let's go ahead and do that. It's going to be F, is that capital F? Yeah, over m divided by L. Okay. So we've substituted in our value for mu, or our formula for mu right here. And then we need to do one more thing. How about we are using this one and we have velocity. We could take the little f times lambda and put it over there. And we don't have it in terms of f yet. When it says in terms, formula for f, we need to do like what we did up here, isolating t. So the next step right here is to isolate f. So that's what we're going to do. Isolate. So I'm going to give you a second to work on that one. Give you a second. I'm going to put parentheses that'll help you, I hope. If you need help with this, this will help you get to the next step. What are we going to do to get into that Who knows what that first step will be? To get rid of the square root, what do we need to do? Yeah. Square. And then we end up with f squared, we end up with lambda squared, and that's then equal to f. I'm going to go and multiply it by L over m. Why did I do that? Because it was dividing by a fraction. It was f divided by something, right? So if it's f over 1 divided by m over L, what can we change that into? Multiplication. So that's how we ended up. Okay. From there, I think you're ready to go ahead and do one more step in solving for f. I'm pretty sure we want to get rid of that. And check the number once you get up. Okay, we need to get f by itself. So what can I multiply to get rid of this fraction? Multiply by m over L. Both sides. And I'm going to just rewrite, since those are going to cancel. I'll rewrite it like this. F force. Sorry, force, that's not tension. M f squared, lambda squared, that could have been kept together if you'd like, but we end up here. You could have had little f times lambda squared as an expression squared. Good. You see what we're doing though? You see, it's not actually finding the wavelength for a certain node or frequency. The closest we'll get is number 2. How would you keep the tension the same if the frequency changes from 275 cycles per second to 400 cycles per second? So this is actually pretty interesting because have any of you changed the guitar string? You know, what you do, right? What you do so you know you're not going to pop it is to like pluck it while you loosen it so you hear it going down, right? If you turn it the wrong So this is talking about frequency change. The frequency is related to the tone, right? Like an A is 440 hertz. Yeah. So you know that we're talking about a tone changing. And that's talking about how would you keep the tension the same if the frequency changes from here to here. We're going to have to accommodate it by changing something else. We'd have to either change the length of the string, right? The string length. We might have to change the mass of the string. But those things count. That's important. I was at a festival once where they had a stringed instrument, but the strings were like 40 feet long. It was like anchored into the ground over here, and it was going over you. People could walk underneath inside the instrument, and if you plucked it, it was like the lowest tone you could hear. And then there were some that were higher tones. It was interesting. So first, how about we see this? What factor did we change our cycles per second? Looking at this, did we double it? No, that'd be too much, right? So it's probably somewhere between 1 and 2. We didn't double it. We got to find how much higher we made this frequency. So what could we do? What do you think? Good. And I think it's still here. I can see it. 1.45. Okay. So that's just talking about the factor in which we made it larger. Okay. So now, since that's the factor that's changed, we're going to end up with this formula over here. We're going to have excuse me, where's that? The mass times 1.45 F squared lambda squared over L. That's why I split them up. You see that in the back? Good. You split them up there just instead of F lambda squared. So what would you need? How would you keep the tension the same if the frequency changes? Okay, so we're going to actually make this equal to, where did tension, oh yeah, I keep reading the F is not force. Tension, force? Maybe. Strain on it. I don't know if it's more related to, I don't know. I've taught physics for years. We're going to keep F the same. So if we have 1.45 F squared, what's something we should do first to know what we gotta change? What's something we could do here? Yeah, what is 1.45 squared? What do we get? 2.1. Thanks. 2.1 F lambda squared over L. Okay. So if I want to keep this tension the same, what do I need to do? What could I do here? I can manipulate lambda. I can manipulate the mass or the string length. So go and work on this with a partner. Double check what you could do here. It's to keep the same balance that we started with. Well, we changed, right? We changed the F by this factor. We're at this point now. But I need this to be balanced. Right now it's saying that the whole thing is 2.1 times larger. So what do I can manipulate any of these other variables by doubling it, by dividing it in half, in order to multiply it all together and get back to where we started. I look here and I have 2.1 F, right? 2.1 F. So does anybody have an idea what to do? It's easier to figure out from doing it. Yeah. Good. So watch what happens. If I go in here and for the L, or string length, I put in, well, I'm going to make that 2.1 larger. Right? All these are multiplied together. N times 2.1 times F times lambda. So I'd be able to cancel out this 2.1. hard to explain because we are accommodating this in order to keep our tension the same. But if we change this frequency by a certain factor, the tension is automatically changed, right? So we're just seeing how do we avoid that happening. Okay. It is abstract right here. It's explained. Just ain't gotta reduce the velocity of the velocity of the wave, the lambda, the wavelength. Reduce that to 2.1. Because we're going to square it. Right. It may be that actually we need to end up with something like this. Let's see, almost. How about this? Would that work? Because 1.45 squared we did, squared and got 2.1. You see how it's going to work? Because we are dividing it by that proportion. Okay, that's another example. Anyone else have a third? So yeah, that will keep our tension the same. Good. That's another one. Do the same thing with mass, and it would be a little bit different because we don't have a squared value for mass. So how about we do? What do you guys think? 1.45? 2.1. The reason why is we divided by 1.45 here because we were going to have to square that variable. Over here, mass is not being squared, so what I could do is just divide it by 2.1. You see that situation, we don't have to square our mass, so it's just going to cancel off right off the bat. Little detail. How do we feel? This last part's hard, but overall, in substituting, rearranging, how do we feel? Thumbs up, sorry, after that part? Okay, okay. So there may be one problem that's a little challenging with this, but ignore the problems with it. So you guys have a good amount of time, all 9 of you. Election days. Yeah, you have. Oh. We're out of here 1:13, huh? Okay. Well, you do have about 8 minutes. I say you get half the homework done. It's on page 33. Page 33. And it's 2 through 10 even, so it's really only a few problems. Because some of them take a little bit of time. All right, thanks for watching.